For example, now we have 7 variables. So in practice, we would like to find the subset of X variable, subset of these 7 variables that can, when we put into the model, and yield the highest R square. Okay. So the thing that when we have the larger R square, the better the model. Okay, basically. And if you look at the formula of R square, you can see that the R square can range from 0 to 1. Okay? R square can range from 0 to 1. However, there's some drawback of R square. Actually, if you keep adding explanatory variable in the model, your R square will increase and increase. Okay, so that means that if you would like to compare two models, you want to find a better model between two models. But one model might have, let's say 5 variables, but the other model has 3 variables, then you cannot compare R square. Because R square from the model that have more explanatory variables in it, usually we get a higher R square. Okay? So people try to think, they introduce another way, which is called adjusted R square. Okay? The adjusted R square provide help improve the R square and eliminate this drawback. Actually, if you include the explanatory variable that is not have the relationship with y, probably you get the lower adjusted R square. Okay. So the bottom line is that suppose that you have model. Suppose you have two models and you would like to see which one is better. Okay. If you have, suppose the first model you have k equal to 5 and same thing for the model 2, then you can use either R square or adjusted R square to see that which one is higher. Okay. And these two must be consistent when k is the same. Okay, so you just pick the model with a higher R square or adjusted R square. But suppose that suppose model 1 has k equal to 5 and model 2 has k equal to 3. We mentioned that R square is not appropriate, right, anymore. So we're going to compare only the adjusted R square. But there is no clear interpretation of the adjusted R square. Not like R square. Okay. And in XPSS output, you can use either ANOVA table or model summary table to find R square and adjusted R square. For the model summary, they put the R square and adjusted R square directly, right? But in ANOVA, if you would like to find R square, you have to use SSR, which is this one, and then divided by SST. Okay, and then you get the same thing. So how to interpret the R square? R square can range from 0 to 1, right? When it crosses to 1, it's better, right? The higher, the better. So here we have R square equal to 0.257. Okay, so we can interpret that 25.7% of the variation in income is a Y variable. That 25.7% of the variation in income is explained by the 8 independent variables. Okay, so that means that 74.3% remain unexplained. So our model is not, this model is not good. Right? You expect a higher R square. But in practice, it depends on the context. Like for the social science, many people get the sample survey, okay, and perform regression analysis. Usually, R square for those models are very low, maybe 0.4 or 0.3. Okay. But sometimes I found that R square can be pretty high, like 0.8 or 0.9.
In this case, how can you get 74.3%?
Okay, so this is a 25.7% that can be explained. So this is just 100% minus this one. So it gets 74.3.
Cannot explain by this model.
And the last one, the last condition, we have 3 conditions, right? The first one is a standard error. The second one is a R square and adjusted R square. And the third one is to test the validity of the model. Okay? So to test the validity of the model, we have to form this null hypothesis. Okay, that all the slopes are equal to 0. Okay, and then one is mean that if we reject the null hypothesis, that means that we have at least one beta J is not equal to 0. Okay. It doesn't mean that all of them is not equal to 0, but there is at least one beta that is not equal to 0. Okay. And how to test this null hypothesis? We're gonna use the ANOVA. Okay, we're gonna use the ANOVA. The test statistic is right here. The F value. We're going to use the F test statistic right here. And this follow, this test statistic follow the F distribution with K and N minus K minus 1 degree of freedom. We always use the degree of freedom for the error. Okay? When this is to test beta 1. Again, we don't include the beta 0. We don't care about the interceptor. Okay? So we use this test statistic. But suppose that we test one at a time, right? One beta at a time. We mentioned that we use t-test statistic. Okay. And the degree of freedom is actually n minus k minus 1. When we talk about the coefficient table, we mentioned that we have the t-test statistic. And this test statistic, each one, follow the t distribution with n minus k minus 1 degrees of freedom. But the F test statistic follows this F distribution with degree of freedom k and n minus k minus 1. Okay. In the similar to when we did ANOVA. You still remember ANOVA? The exam is 2 weeks from now. Okay. So when we talk about ANOVA, what is the objective of performing ANOVA? Compare the mean, right? When you have more than 2 populations. And when we construct the ANOVA table, we also obtain the F-test statistic. But then, what is it? But the F-test statistic, the rejection region for this test is on the right side, always on the right. And it's same as here, okay? Same as here. So we're gonna reject the null for a large value of F, okay? We don't have rejection region into the side, but we have rejection region when F is large, okay? We reject the null. We reject the null hypothesis when F is large. Okay? And in SPSS, I also put the p-value. So the p-value here is one-sided or two-sided p-value. One or two? It's one-sided p-value, right? Because we reject only for a large value of F. Then the rejection region is on the right? So it corresponds to the one-sided p-value. Okay. Here we have one-sided p-value equal to 0. What does it mean?
Reject.
That means that our model is good or bad. Can that's when you reject the null, okay, for small p-value we reject the null hypothesis, right? That means that there is at least one beta is not equal to 0. So what does it imply? Whether our model is fit data or not? Yes, right? That means that at least one x can specify y. Okay? So our model is fine. Okay? So we're going to use the combination of these 3 conditions to assess our model. Okay? So if we get the perfect model, okay, if we get the perfect model, we must have the large value of f, right? Like infinity. And then r squared should be equal to 1. Okay, so we have the highest r squared. And then the standard error should be very small. Okay? For example, for perfect model, we probably have 0. But in practice, we're not going to get this, right? We're not going to get this. Okay, before we talk about the in the middle table, we go for the useless model. What is the useless model? That means that we should have a very large value of standard error, right? R squared is 0. That means when R squared is 0, what does it mean? How can you interpret it? 0% of variation of y can be explained by independent variables. That means that 100% are explained. It's not good. Okay? And then we have the f value which is 0. Okay? But normally change we're not going to get perfect model or useless model, but somewhere between. Okay? For the good model, we should have large F value, large R square, and then small standard error. Okay? And for model, we have small value of F, small value of R square, and then large value of standard error. Okay? So we're going to use this combination of these three conditions to assess model fit.
How can we decide that it's a large or small of F value?
F is
How can we decide it's a large or small or it's a limitation?
okay, that's a good question. How to assess whether standard error is small?
I mean the F value is
F value.
Yes.
Which number is large, which number is small?
What do you think? What do you think? How to check whether F value is large or small?
Depend on critical value.
Yeah, it's based on critical value. If you can find the p-value, you can check for the p-value. If p-value is very small, that means that you have very strong evidence against the norm, right? That means that you have very strong evidence against the norm. What does it mean? Okay.
If F is large, p-value is small. Yes.
Okay.
So compare to the P value.
Yeah.
When we learn about hypothesis testing, right? We have now hypothesis versus alternative hypothesis, right? And then what is the definition of p-value? Okay. You said that you use p-value to make decisions whether you're going to reject the null or not, right? If p-value is less than alpha, then you reject the null. If p-value is greater than or equal to alpha, then you fail to reject the null. Okay? Then, suppose that you reject the null, how can you conclude? How can you draw a conclusion?
At least one. At least
There is enough evidence that
at least
H1 is true, right?
yes.
There's enough evidence that H1 is true. Actually, when you mention about that enough evidence, okay?
No, not F1 is true.
Now you have enough evidence, but how strong is your evidence? It depends on p-value. If you have very, very small p-value, that means that you have a very strong evidence. Okay. For example, think about it. You have alpha equal to 0.05, but your p-value equal to 0.045. You still reject it now because you have enough evidence. But this kind of close to the cutoff point, right? Then this is not a strong evidence. So when you have smaller p-value, you have a strong evidence. that is go to the H1.
Yeah, one question is, yeah, why don't you care about B0?
Beta zero.
Yeah, beta 0. Why? What's the
Okay.
reason?
So the question was
Yeah. Okay.
why don't we care about B0
Yeah.
or beta 0?
Why don't you?
Can anyone answer? Me? Why we do not care beta 0? Anyone would like to answer? Yeah, in the back. And I give you a microphone.
Because we're just trying to check like the variables that were chosen is okay or not. So that's what we just we want to do.
Okay. Because you would like to check whether your model is good or bad, and or your belief is your belief that the x variable has a linear relationship with y. That's why you would like to test the slope, not the intersection.
But finally, we will draw like a equation with the intersect, right?
Yeah, normally we draw a regression
Finally,
with
intersect value.
the interceptor, but we usually don't force beta 0 equal to 0. We don't. Okay, so. Suppose that you got this table, right? You see that some of them has a p-value greater than 0.05. Some of them has a p-value less than 0.05, right? So basically, if you got a result like this, normally we remove this variable. We remove we remove the variable that has a p that is not significant, basically, and then we refit the model. We have to refit the model to get the new estimate for all. Okay? And normally in practice, I mentioned that we usually don't force interceptor to 0 because it's not natural, unless that you have a strong belief that the interceptor is 0.
Okay. For this question, if the significant value for the constant is like a 0.1 because
0.1.
okay, it's greater than the p value.
We just ignore that.
Yes, it's not.
Yeah.
Yeah, why?
Why?
There's a main and there's a white.
Yeah, if you don't reject. But it's okay. It's okay. Can discuss next. Let's move on. Yeah, later. I wish.
When you interpret what is the interpretation of B0? It's the average of Y, right? When x equal to 0. Right? That's it. I mentioned that if you have the strong belief that y bar equal to 0, then you can force the intercept term to 0. But otherwise, you shouldn't force it to 0. I cannot think about an example right now.
Okay, I will
But
see
then-
discuss later.
Okay, we can talk after class.